Welcome to Star Talk All-Stars. I'm Jana Levin, your All-Star host for the day. I'm an astrophysicist and author. Joining me as co-host is the funny Matt Kirshen, host of Probably Science. Hi, Matt.
Jana. How's it going? Yeah, it's nice to be here in space.
It's great to have you. And I also want to introduce one of my favorite people in the world. Joining us in the studio, Ray Weiss.
Oh, thank you, Jana.
Otherwise known as Rainer Weiss, for long. Great to have you. Ray is Professor Emeritus from MIT. He is also one of the original architects of the LIGO detector, which announced the detection of gravitational waves, one of the most groundbreaking discoveries of modern astrophysics and very personally important to me. Ray is one of the founders of the LIGO instrument and continues to work on the instrument all the time, as I know because I've been to the sites with you. You kindly let me perform.
You slogged
very
with
modest.
me in the tunnel, I remember.
Yes, in the heat of Louisiana. It was amazing. So it's so great to have you here. We're going to talk about LIGO and gravitational waves and black holes. So I think what we want to draw out is why this discovery was so important. I think that when people heard about it, it was though the whole world stopped in February 11th when the announcement was made. And for a minute, it was so exciting. Everybody was frozen. And then I felt like an hour later, people just weren't sure what it was all about. It's hard to understand.
I mean, I've got it covered because I'm obviously good on these things, but just for everyone else, if you could just kind of give a vague overview.
Well, I'll try, but I was as mystified as you in the fact that it had this enormous public recognition.
Oh, yeah.
I mean, you take other things.
Were you surprised? So
I was more than surprised. I was flabbergasted, to be honest with you.
Oh, really?
I mean, my first real instinct that it had permeated the society was when I came to New York to come and visit you at the Pioneer Works.
Yeah.
And I get in the subway, and there's this sign that says, scientists can find gravitational waves, but you can't find an apartment in New York with a walk-in closet.
Right.
I said, where in the hell does that come from?
Yeah, exactly.
And then
it was a Jeopardy question.
Is that what it was? Okay.
Yeah, no, also, as well.
Oh, I didn't realize that. I didn't realize that.
Has science now detected an apartment in New York with a walk-in closet?
I haven't been looking lately, but I don't live here.
If anyone can find it, Ray can. So, Ray, do you want to tell us what gravitational waves are? Because this is very hard for people to understand. They can say the words, but they really don't get what it's all about. And they certainly don't get why you played it to them as a sound.
Well, let's start with what they might be. I mean, what they are. They're a result of Einstein's first thinking about how you measure things in space and time. In other words, he realized back in 1905 that the Newtonian theory we had, the theory that we all learned in high school, was inadequate. That you couldn't have things travel so fast that everybody knew about it instantaneously. There had to be some delay, because the fastest that things can move, even information, thought, is the velocity of light.
Right, so if the sun disappeared tomorrow, it should take us 8 minutes.
Well, that's right. If the sun disappears, it'll take about 8-9 minutes before we really know about it.
It's great if you're like a magician or something.
What, do you need the extra time?
Well, yeah, because
8
like
minutes
David
is a long time.
made the Statue of Liberty disappear, but he had like seconds really to do that in.
Yeah, if you had 8 minutes to play with,
anything. Like, you could be an amateur magician and still kind of like, you'd have time to get some helpers to actually shove it out of place.
What'd you do with the sun, Matt?
Yeah, but those 8 minutes are damned important.
Right.
Because they tell you that there has to be some mechanism for information to travel not infinitely quickly.
Right. So in Newton's theory, it would happen instantaneously.
That's the first order way of talking about gravitational waves. Then specifically, what are they? Einstein had a different way of looking at gravity than Newton did. And he taught us all that space and time get distorted by gravity. You get curvatures, you get distortions of space and time. And what a gravitational wave is a traveling distortion of space and time, but we measure it as a distortion in space. And a very special thing, so you can imagine what it is not very hard to imagine, is that it's a stretching of space and a compression of space. And just bear with me, here's what it is. Where the wave travels, let's say, toward you, and it does its dirty work, perpendicular to the direction in which it's moving. So something's doing this. And while it's doing this in one
Ray's
dimension...
oscillating his hands in and out.
Oh, yeah, I got to tell you, that's right. Like waving my hands back.
Almost like a slinky spring.
A slinky, let's say a slinky in the X direction, but a slinky inverted in the Y direction. It's doing the opposite.
I hope you all use right-handed coordinate systems.
In one dimension, in the direction it's moving, perpendicular direction it's moving, it's stretching in one dimension, it's compressing in the other. And that continual compression, expansion, travels at the velocity of light toward you. And that's the way to imagine a gravitational wave.
Now, when you first started thinking about this, You were a young professor at MIT, and you had this whole gravity research program. And I know you confessed to me that they asked you to teach a class in general relativity.
Well, I'll confess again. What Janet's referring to is a very big embarrassment. See, I come to MIT having been to Princeton, the hotbed of general relativity and gravity, and I come and I start a group, very experimental. I'm an experimenter. I'm not a theorist like Jana. Jana is a true theorist, but I'm an experimenter. I deal with things with my hands, and what
already, like, before the show even started,
he was using his hands.
Well,
wildly.
yeah, before the show started, you were kind of looking at the microphone and like taking it apart. Like, you can't help yourself.
No, you can't.
Switchboard.
Yeah, you got to do that. You got to find out what you're surrounded by. Come on, that's part of the world.
Yeah, palpate the world.
So it's tactile and it's all sort of seeing things. But anyway, so as Jana says, that what happened is that I'm running this group that is supposedly about very complicated topics like cosmology, which is the history of the universe, and also gravitation. Okay, those were the two things I started. And then the department head comes to me and says, we would like you to teach a course in general relativity, which is a course of the new kind of gravity. And I couldn't tell them I didn't know a damn thing about it. I mean, I really didn't know much about it. I didn't know the mathematics. I mean, the students, when I finally started teaching, were probably I was barely half a day ahead of the students, if at all.
Right.
Okay? So here I go, and they ask me a very hard question as we go along. The course has its ups and downs, as you can well imagine. And they asked me a hard question. They said, look, what is a gravitational wave? And I tried to answer it. But what was going on at that time was that Joe Weber, who was a physicist at the University of Maryland, had begun to talk about that he might have discovered gravitational waves.
Mm-hmm. Okay. And his campaign started in the 50s to...
No, this was started in the 60s.
60 to late 60s.
Well, he started really quite early, in 62, and he made the announcement that he had discovered gravitational waves in 1969. That caused a tremendous furor.
He was incredibly famous.
Right.
Well, yeah.
And he was lying? He was just...
No. Don't say lying. That's not the right word.
We're all very defensive about Joe now.
It's like, I don't want to brag, but I also did discover gravitational waves like about a month before you guys.
That's good. I'm glad of that. What did yours look like?
It was like I just put a cup on a like, kind of wobbled a bit.
And the water wobbled, and he knew that they were gravitational waves.
It's like those
Jurassic Park.
Yeah, well, like those two birds in the New Yorker cartoon. Probably saw that cartoon.
I didn't see it.
Two birds sitting. This is right after the discovery again. Two birds sitting on a branch. It was on the 12th of February. We announced on the 11th of February. So somebody had prior information.
Right.
But these two birds are looking. One looking at the other, and for one says, "Hey, did I hear you, or was that a gravitational wave change?" And that is already, that's the kind of thing. But anyway, so let me get back to the story. The thing was that they asked me about this, and I frankly, be honest with you, despite having trouble with the mathematics, I also had trouble with understanding Weber's experiment. It's not that he was lying or anything like that. It's just a way too complicated for me to understand exactly what he was doing. So I spent a lot of time one night thinking about how could I explain what a gravitational wave does, and how would you detect it in the most pristine, simple-minded way possible. And that's where this haiku, as you call it, came about, which is I thought, well, one way to do it is send some masses out there, put them out in outer space, put clocks on them, two clocks, one on one, clock on the other, and have a light beam go from one to the other and measure the time. That's all.
Yeah.
Very straightforward measurement.
And they'd have to be sort of floating, so that
floating out there. I mean,
like bobbing on the wave of the ocean. If something.
Well, they're actually just moving along without any forces on them, and then all of a sudden a gravitational wave comes along, and it changes the time that light takes that goes between them. That's it. Makes it shorter for a while and longer. Does exactly what the gravity.
You started to build one.
Well, yeah. But that's the basic idea. And by the way, that idea is the one that propagated into the later on LIGO and everything else.
Is this what you wrote about in your book? Is this what?
Yeah. So I was fascinated with, you mentioned Ray looking at the microphones and all this stuff. I was fascinated that Ray said that he started life with one ambition, which was to make music easier to hear.
That's right.
And then you dreamt up, which is basically a cosmic recording device, sort of insane, gigantic cosmic recording device to record sounds from space.
She was the only one in my whole life who ever made that analogy, and she was right. I told her the story.
Awesome.
And because I think you have a musical background, or around you is music, and understood this right away.
Yeah.
But it's absolutely true. It was.
Yeah. So
what's the book called?
Black Hole Blues and Other Songs from Outer Space. Which, if I was Neil deGrasse Tyson, I would say in an awesome, deep DJ voice. I think I do have him recorded saying it. I should air it.
You just play that in at that point.
Right. Exactly. Just edit that in. Now, you were really hoping for the centenary for the first detection. So here you've been building this thing for 50 years, Ray. I can't tell you how many times somebody said to me, we better go ask Ray. On site, you're doing experiments, you're walking the beam tubes, and you want it to be 2015. You wanted that so badly, I know. And
16 or 15 was good. 16 was the latest.
Okay, so you were willing to take 16, and then if not that, you would find an Einstein paper that was,
It's a 2018 paper, but that was it.
No, a lot of people told me 2018, don't expect a detection before 2018. Yeah. But on September 14th, 2015, yep. This struck. It must have blown your mind. I mean, what is the experience of waking up that morning and checking the logs? Yeah. And
I remember thinking it was the practice run that wasn't meant to be the run that detected anything, right?
You're absolutely on the mark. That's correct, yeah. It's even worse than that. What happened is we didn't expect this, and when, as Jana points out, I happened to be on vacation. I had been at the site the days before that. And so you asked, what did I think?
Yeah, you check the log. You wake up 8 a.m. in
Well, I'll tell you what happened. It was really cute. I went to the log. We were on vacation. My wife and son were with me, and his wife. And I was looking at the log, which I do every morning, and I see this thing, which was very cryptic. It says, we're canceling a Fix-It Day. Now, we have Fix-It Day every Tuesday. We are running in the middle of a run, even in an engineering one. When we find all these things wrong, we don't want to mess with the apparatus, but we do it at a certain time so both sites are dead at the same time. And they said, no, we're canceling it. So I look at the other site, same damn thing. We're canceling Fix-It Day. So I call up, what's going on? And they say, well, and then it didn't take long. I began to get email. And then very quickly, within about half an hour after that, I saw an absolutely magnificent curve, which was this signal, which now is on people's dresses. It's in everywhere. And it was this binary black hole, 30 solar masses. And I look at it, says, holy mackerel, this has got to be a fake.
Is it really mackerel that you said?
Yes. Well, maybe not. I'm trying to be careful.
He's cleaning it up for air. If I know you, Ray, that's not what you said.
Gee whiz.
No, none of those.
You're a 1920s paper boy. Say, mister. We got the scoops.
It was really something when in February, all these months later, the announcement was made and everybody just shared in this incredible excitement. That was really a moment in history.
And it was, we did a lot of work between the time we found it and then because we didn't believe it. Yeah. Let's be honest. I mean, Jana, that was such a big signal. We never expected such a big signal.
Amazing. So I think that's an interesting place to end, and I'm really sorry we have to wrap this up, but I'm glad we're going to come back in a minute. We're going to take a short break. Stick around for more discussion and more of your cosmic queries after this. In and out and in and out and in and out.
Did you do it again? Leave your holiday shopping to the last minute? Well, the good news is we've got plenty of fan-designed shirts, official Star Talk mugs, tote bags, and hats in our online Star Talk store. You'll find exclusive cosmic jewelry posters, the Star Talk book, and more. The better news is that you can continue procrastinating for a little while longer. You can order as late as December 19th with our 3-day shipping option or December 20th with our 2-day option if you're a super duper last minute shopper. Admit it. You know you are. You know you're probably going to wait until December 22nd and get your gifts thanks to our next day shipping option. That's probably what's going to happen. Even so, you might not want to wait that long. Some of our most popular items and sizes are already sold out. Just click shop at StarTalkRadio.net and have your Star Talk favorites shipped right to your door just in time for holiday gift giving. This year, why not give the science fan in your life some Star Talk, even if that science fan is you?
Bringing space and science down to Earth. You're listening to Star Talk.
Welcome back to Star Talk All-Stars. This week's special edition is a hodgepodge of some of our favorite discussions from the past 2 seasons. Here's more of this week's mashup.
Welcome back. Bill Nye here with Chuck Nice on Star Talk. And this week is Star Talk All-Stars. And I'm the guest host. Mistakes are made. I'm the guest host, all-star host with Chuck Nice, and the Cosmic Queries are where we take your inquiries from anywhere in the cosmos.
That's right, anywhere in the cosmos.
You can be anywhere in the cosmos. If you can get on the Earth's internet and send it in enough English characters or Roman characters arranged in English language, we will do our best for you.
That's right, because in the end, it's all zeros and ones anyway.
It is. Yep. It's troubling but empowering.
Hey, here's Shane Henson from Facebook who says this. Hey, Bill, my question is, what invention from outside of science has made a large impact within science? Has an invention built to serve a different purpose other than science been used to advance science in new avenues of thought or discussion? Shane Hansen from Lethbridge, Alberta, Canada. P.S. Bill Nye the Science Guy is what made science fun for me growing up. I still get excited whenever I see an episode. Thank you so much.
Wow. Very sweet.
It was very, and heartfelt, right?
Yes.
Yeah, I mean, this...
I'm palpitating. So what is outside...
I think there's a pill for that. I think I take it for my heart.
What is outside of science?
So I guess what he's saying is, has there been kind of something that wasn't a scientific endeavor that led to a great scientific discovery?
Well, I mean, nuclear weapons.
Wow. God, that's not the answer I wanted. Well, I mean, even though you're right, that makes sense.
Trying to understand the inside of atoms.
Right.
Led to, let's call it nuclear power.
Nuclear power.
Feel better?
Thank you, yes.
Some of the energy right here, I think it's 19% of the energy in New York is made nuclearly.
Yes. As a matter of fact, we've just found out that the power plant, which is not very far from where we are, is not adequately protected.
I'm shocked. No, everybody, I'm not changing the subject. The nuclear industry just hasn't been that great at safety.
Yes. What is that about? I mean, seriously.
Well, they got in a hurry, and plus, it just seemed like such a great idea. Dig this stuff up, fission it, make electricity, put it back in the ground. What could go wrong?
Exactly.
Stuff goes wrong. Anyway, that aside, what invention came from outside of science? I mean, it depends what you want to exclude.
What do you call an invention?
You know what do you want to exclude? But to me, the greatest go ahead.
Has there been like some, I don't know, crazy cooking discovery that led to something in the medical world? You know what I mean? Like, we found that by cooking the bark of a certain tree cures this particular ailment.
Oh, that's
and then we were able to distill that essence and make a pill out of it. Something like that.
Willow bark became aspirin.
Get out! You're right.
Yeah, but is that...
I forgot about that.
Were the willow bark investigators and investigatrices, were they not doing science?
You know,
some level?
I would assume they were.
Have lab coats and business cards that said science person on it?
That was a long time ago, too.
Well, and it worked. And when people say, what's the greatest invention? I almost always reply, sewers.
We've had this conversation, but, and we'll get into that because I have
Let's not get all the way into that.
We won't get all the way in because I have somebody, I don't want to steal it from them, but the last time we had a conversation, you told me sewers and I was flabbergasted.
You were still gasting a flab.
I'm still gasting a flab. And I got to tell you, when I heard your explanation as well, I was like, holy crap, I'm sorry.
And he did it again, people. Comedy is natural for him.
See that?
He doesn't even, it just
boom.
Just happens.
It happens like that.
Enough with the verbs. Yeah, so, anyway,
but yeah,
what's from outside of science? Is willow bark from outside of science? Is fire making from outside of science?
Right.
I don't know. Second law of thermodynamics, I'd say, is inside of science. Timekeeping, we talked about earlier.
Yeah,
timekeeping
is science.
Coffee making, is that chefing or sciencing?
See, there you go.
Either way, it's delicious.
So true. Now I want a cup of coffee.
I really recommend, if you guys out there are going to start a radio show or podcast, I really recommend you have a coffee pot. This is not extraordinary. This is not an extraordinary idea.
It's a simple thing, right?
It's very common.
Very common.
Lead on.
All right, here we go. Well, Shane, good question. We didn't really get to an answer, but yeah.
Well, it's a tough one. I don't know what's outside of science.
Yeah, what's outside of science? Everything is science when you think about it. So
that's what we're saying.
That's really what we're saying.
That's what we're saying.
Everything is science. Okay. All right, here we go. Grant Roach says this. Hi, Mr. Nye. What 3 key inventions do we need for a manned mission to Mars?
Which could be a human mission. It doesn't have to be guys.
It doesn't have to be guys.
I mean, if I'm going out into space for 400 days,
right?
You're a great-looking guy, Chuck, but I wouldn't mind having some ladies.
YMCA. Okay.
You can... there's no need to feel down. Pick yourself off the ground.
That's right. You can get yourself clean, baby.
You can have a good meal.
You can have a good meal.
You can do whatever...
you feel.
At the YMCA.
There you have it.
So with that in mind... I don't know why this person chose 3 key inventions.
This is what I just read them, Bill. But he says, what 3 key inventions do we need to send some Mars, some astronauts to Mars?
So at the Planetary Society, as you may know,
yes,
we did an analysis last spring.
Mm-hmm.
We don't really need any new technologies, new inventions. We just need to improve or literally expand the technologies we already have.
Okay.
And the expansion hilarious reference I was making was to the inflatable habitat.
Aha!
So you have existing rockets, you get in orbit, then you fly some more rockets up to get enough fuel, and you fly to Mars in a big inflatable habitat, and you orbit Mars. And all this could be done with existing technologies if it was just decided to be done. So the analysis we did at the Planetary Society was 2033.
All right.
Now, if you're of a certain age, Chuck, as I am, you remember the Apollo program, and astronauts orbited the moon first.
Yes.
Apollo 8, 1968, orbited the moon, and that was the precursor. That's where it figured out trajectories, made sure the retro rockets retroed and rocked, and took the famous picture of the Earthrise on the eve of Isaac Newton's birthday, 1968, astronaut Bill Anders.
And they call that what? A moon orbit insertion? What is that?
That's the lunar orbit insertion.
Lunar orbit insertion, right?
Yes.
Okay, cool.
Space people dig that.
Yeah.
So we could do the same thing at Mars in 2033 without increasing the United States National Aeronautics and Space Administration, NASA, budget. If you got international partners, if you got motivated, Lockheed Martin thinks they could do it in 2028, which would be 2 Martian orbits sooner. And we're all for it. Let's go. But the things you need is a place for people to live for this journey. You need great big rockets.
Right.
And you need to decide to do it. And the biggest problems are political.
Yeah. All right. So let's move on to our next.
Lead on.
This is Bert Wardwell. I like your name, Bert. Bert Wardwell from Facebook says this. In recent history, the last 100 years or so, what has been the most important invention or breakthrough that has not had a direct military national security application? Thank you.
Maybe genetically modified crops.
Ooh.
But don't we feed the military with food?
Well, we do.
So maybe
but we feed everybody else with food, too. So they're just lumped into that group, the military.
Lumped in.
Unlike like my mashed potatoes.
But I think it has a cynical quality to it, that query, doesn't it?
Yes, because what he's saying is basically, unless we're making something to destroy one another, we really don't tend to have advancements.
Here's an example from my own experience. I don't know if this will really do it for you, Bert. But I lived in the Pacific Northwest for a long time. We were very proud that it's the hypothermia capital of the world. Because the air is so moist. Any time of year, there's so much moisture in the air, it just sucks the heat out of you. Moist air conducts heat, or water conducts heat 25 times more strongly than air.
That's why wicking technology is so important.
So we had this state-of-the-art technology at first was Filson, which had this tin cloth, they call it, this waxed cotton cloth, and moisture will pass through it. I have a Filson hat from the 1800s.
Nice.
Same technology.
Okay.
Now we have Gore-Tex and the derivative products. All right, so when I went to do the Science Guy show in a Navy airplane.
Nice.
It was cool. We did the Navy training. I swam around the pool with boots on. I wore a flight suit. It was just so cool.
Yeah.
But then the Navy had this very primitive keep warm technology. When you have to parachute out of your fighter plane over the middle of the ocean
Okay.
and get in a rubber raft and hope somebody finds you.
Right.
It was all this very heavy wool. But now the Navy has Gore-Tex.
Right.
So which came first? Bert. I say the moisture-wicking technology came first. That's what I say.
Well, there you have it. Wow, that's pretty cool, man.
I'm jamming there. I'm working hard because that same Teflon stuff is used to insulate wires in aircraft because when it burns, it doesn't make very much poisonous smoke.
Wow.
If it isn't one thing, it's something else.
Something else. That's the world's a dangerous place. That's what we're learning here, people.
You're listening to Star Talk.
It's a trap!
This is Star Talk All-Stars. I'm your all-star host, Emily Rice. Some of you might know me as DJ Carly Sagan, but in real life, I'm professor of astronomy and astrophysics at the CUNY College of Staten Island, as well as a research associate at the American Museum of Natural History, where our benevolent overhost, did I say that? Our benevolent overlord is the director of the Hayden Planetarium. And I have with me in the studio my comedic co-host, Chuck Nice.
Yes, Emily.
Thanks for being here.
Of course. How are you?
Good. How are you?
I'm doing great, and we should introduce our guest.
Yes, this episode of All Stars, we're going to delve into one of the hottest stories of the year, the discovery of the TRAPPIST-1 system and its 7 exoplanets. To help us with that, we've got a very special guest today, David Kipping, who's a professor of astronomy at Columbia University.
Hey, greetings to all you Star Talkers out there across the space-time continuum, wherever and whenever you are.
I love that.
We're not talking to an amateur here. So you're a research astronomer. We'll get to that.
Yes.
Before we take our first cosmic queries, let's take a second to talk about exoplanets. This is your research area of expertise, right, David?
Yeah, this is a pretty epic discovery. It kind of hit a lot of us out the blue. We'd only just recovered from the news of Proxima Centauri having an Earth mass planet around it.
Yes.
And then this discovery sort of not just goes one better, but 7 better. Has 7 Earth-sized planets.
But it wasn't even, so we knew about this planet, this star and some of these planets beforehand, right?
Yeah, that's right. There was, I think, 2 of them had the orbital periods. They knew that those planets were there, and there was a hint of a third signal in there. And then they got some time on NASA's Spitzer Space Telescope, and they observed the star continuously for, I think it was something like 500 hours, which is a lot of time.
That's a lot of time.
And they saw, just transits everywhere in this star. It's just full of transits.
It's a transiting system, so we know that these planets are there. Why?
So what's happening is there's each of these 7 planets is passing in front of the star, blocking out some of the light for a short amount of time, and it's happening periodically. So the orbital periods of these planets, their year is very, very short compared to the Earth. The Earth's 365 days. These planets are more like sort of 1 day up to maybe 2 weeks. And so every couple of weeks, you're seeing like a bunch of these planets pass in front of the star, and loads of dips all over the place when you look at the brightness over time. So that's how they found these things.
Awesome. And you study exoplanets, right?
That's right, yeah.
What kind of exoplanets do you study? Do you study these types of exoplanets or different ones?
All sorts. I don't discriminate. All sorts of exoplanets are fine with me. I guess we particularly like planets which we call cool worlds, which we really mean not just like dope. We're not like trying to use it in that sense. We mean like worlds which are at long periods where they are cool enough that they could be, potentially hospitable for life.
Right.
We don't want the super hot ones so much, but they're also kind of interesting in their own
literally
way.
Cool.
Literally cool.
Actually,
yeah,
right.
exactly.
Yes.
And we like the worlds which are far enough from their star. They can have rings, they can have moons, there can be all sorts of extra stuff happening. So
we'll get to that a little bit later.
Yeah,
absolutely.
Should we start with our cosmic
already
queries?
fascinating? I love it. And let's get into our queries. And of course, we have taken these questions from all across the internet, wherever we have a presence. And we always start with a Patreon patron, because they give us money.
Thank you.
So we say thank you.
Science don't come for free.
That's right. And we will give you priority in terms of your query. And what I'm really saying to you people is, we can be bought. So,
For a price.
That's
And
right.
it's not that much.
It's not that much. We can be bought, and we are cheap. So here's the first question, and it comes from Frank Kane. And Frank Kane says this: I've heard that TRAPPIST-1's exoplanets are tidally locked to their star. How do we know that? And what does that mean for their suitability for life? And Frank comes to us from Orlando, Florida. And that's a great question, Frank. An excellent question.
That's a great question, yeah. A lot of people have been asking that as well. I think.
Right.
So we actually don't know for sure that they are tidally locked.
There's no observation, right?
Exactly. Like
Right.
no one has direct proof of that.
So, and just for me as a layperson, when you say that, that observation would be like our moon to the Earth. Like we can observe that the moon is actually tidally locked.
Yeah, and the assumption is this is bad for life because you have one side of the planet, maybe like the American continent, for example, on the Earth, constantly facing the sun all the time, like all the way around its orbit. And the other side might, freeze out because it's going to be so cold. So this is the dilemma that, if you have a tidally locked planet, maybe it's not so good for life. In this case, so the reason why we think they probably are tidally locked is that if you simulate the planetary system on a computer, you let all the planets be freely rotating, you give them random rotation periods. This is what they actually did in the paper. They simulated their orbits and they found that within 400 million years, which sounds like a lot, but on a cosmic timescale is not that much,
not a long
they
time.
are all locked. It doesn't take that long for them to lock. So within, a cosmic blink of an eye, no matter how fast they initially start spinning, they're going to end up tidally locked pretty quickly. So that's why we think they probably are, but we don't have direct proof that they are.
And why do they end up tidally locked?
Yes.
So this is interaction between the star and the planet, basically. So what's happening is as the planet is rotating round, it has a slight tidal bulge from the gravity of the star. So the gravity of the star is kind of it's like a squash ball. It's squashing the planets down into these little ellipsoids.
Oh.
And as it rotates
we have
round,
tides on Earth.
yeah, same thing. As it rotates round, one side of this ellipsoid is a little bit closer and one side's a little bit further away from the star. And the star's kind of pulling on the near side a bit harder. So it's actually removing angular momentum off the planet.
It's literally, not literally, but it would be, it's like a braking system for a planet.
Yeah, it's exactly a braking system.
It's a braking system for a planet.
Gravitational braking.
Tidal braking.
Tidal braking.
Tidal braking.
Exactly.
Yeah, that's amazing.
Yeah.
Wow, that's super cool. And so the implications for life would be, like you said, because and this is, I'm just going to add to your question, Frank, because I've wondered this. When you have a tidally locked planet like this, and let's say that it's in the Goldilocks zone, is it possible, and this is just from my imagination, that there might be a stripe throughout the sphere of the planet where that is the only place where you have habitable life?
Yeah. That's actually, they call that the Terminator, which is a pretty cool name, right?
Get out.
It's the same thing we call it on the moon. I think this is actually a Jeopardy question the other way. This is how you can tell I'm a new parent, is that my husband and I watch Jeopardy now religiously. Just before bedtime. It's fantastic.
Oh, that's so funny.
Not Wheel of Fortune.
So the Terminator is not the bringer of death, it's the bringer of life in this case, potentially.
Yeah.
So, yeah,
We have a Terminator on the moon, but the Terminator on the moon shifts. Right, because we have the moon is tidally locked. That was a great example you used, Chuck.
Right.
The moon is
tidally locked to us.
But the sunlight is coming from the sun. The starlight is coming from the sun instead of from the Earth.
Right.
And so we can kind of think about the moon when we think about these planets, but not really. Because there's the moon, the Terminator moves around the moon. So that would be moving. But with these planets, the Terminator stays put.
Will be stationary.
Yeah, so there is no dark side of the moon. I always like to tell my students that Pink Floyd lied to you. There's no dark side of the moon. But for these TRAPPIST planets, there is a dark side of these planets.
That's actually why moons could be better places. We'll come to moons later.
Okay,
but
we'll
that's
get to
why
the
moons
moons.
could be better
That's why
places.
I'm wearing my moon shirt today to remind me.
Yeah.
But the Terminator would be like perpetual sunset.
Yeah.
Sunrise or
That'd be
sunset,
beautiful.
it doesn't matter
Yeah.
because it's not changing.
Right. Oh, man, that's so cool.
Isn't that kind of cool?
That is really, really cool. I wouldn't mind living in the Terminator zone. No, I wouldn't mind retiring there.
As long as Skynet's not there.
Hey, I want to talk to you about Star Talk All Access for a moment. When we started our premium subscription service, we thought fans would be more interested in getting to watch video versions of our podcast or enjoy ad-free versions of our show. But it turns out our fans' favorite part of All Access is the new and exclusive original content that we post every week. We're talking about classic videos like me and Neil deGrasse Tyson chilling in his office touching his meteorite. Oh, you heard me. Or the time Neil and Adam Savage hung out in the green room before our show at Comic-Con and talked about Star Wars, Blade Runner, A Space Odyssey, and other really geeky science stuff. Star Talk All Access is your universal hub for all the great Star Talk content you crave, all in one place, including full video of most current episodes, commercial-free audio and video podcasts, live-streamed events, insider-only looks behind the scenes, the ability to watch on Amazon Fire, Apple TV, and Roku, and, of course, new exclusive original content added every week. To get started, visit StarTalkAllAccess.com to subscribe for $4.99 a month with a 2-day free trial. That's StarTalkAllAccess.com. And as a friend of mine says, keep looking up.
Bringing space and science down to Earth. You're listening to Star Talk.
Hello, this is Star Talk All Stars Edition. I'm your all-star host this evening. Carolyn Porco is my name, and I'm a planetary scientist and the leader of the imaging science team on the Cassini mission, which is, as we speak, in orbit around Saturn. My co-host today is Chuck Nice. Thank you, Chuck, for being here.
Oh, thank you. It's a pleasure to be here with you, Carolyn, definitely.
Well, I'm so glad to have you. Today, we're going to talk about some of the fascinating discoveries we've made on Enceladus with Cassini. And to help us out in this discussion, we have Chris McKay from the Ames Research Center in the Bay Area. He's astrobiologist extraordinaire. Chris spends his time scouring the deserts of Earth from Antarctica to Siberia, Namibia, Sahara, trying to understand those places on the Earth that might be like Mars in their environment and wondering how life can thrive there. He's been involved in conjuring what kind of human mission back to Mars might be like. This is a mission that would be piloted by humans. He's involved in that. And I've invited him here today because he is my cohort for the last 11 years in trying to get people to pay attention to what we have found with the Cassini mission on Enceladus, which is a small moon in the Saturn system, no bigger across than England, and why this small moon presents to us the most promising environment in the solar system to actually search for life or evidence of prebiotic chemistry. So welcome, Chris.
Thank you, Carolyn. It's a pleasure to be here talking with you.
Yes. So we've gathered your cosmic queries about Enceladus and astrobiology from various social media. That's right, Chuck. Haven't we done that?
That's exactly what we have done. And we have people from all over the internet who have submitted their questions via Facebook and Twitter and you name it, whether it's startalk.net. It doesn't make a difference. We take them. And they all want to know about Enceladus and more. You know, astrobiology and more. You know, people see your name and, you know, some people just want to know about Cassini and some people want to know about Saturn. And so I know that we're kind of focused on Enceladus, but, you know, when you say, when people who follow us, when we say Carolyn Porco, they immediately think Saturn because Neil calls you Madam Saturn.
I'm Madam Saturn. For the rest of my life, I'll be Madam Saturn. It's all right. It could be worse.
It could be a lot worse.
It could be worse.
So let's take our first, you know, we always like to have a Patreon. For those of you who are interested in supporting us on Patreon, by doing so, you get to do cool things like you get invited to parties that we might throw, or you can submit a question for our Cosmic Queries, and we will make sure that we read it because you gave us money.
That's a basic transaction in life.
Right? That's a basic life transaction. You gave us money, and now we're going to do something for you. So this is from Luna McIntyre, who says, do you think there are parallels that can be inferred by whatever is found with the Europa mission? since the liquid oceans on both moons, I suppose both moons, she means Enceladus and Europa, seems to be due to tidal heating. So are there any, first of all, is that the case? I mean, are both moons, are there oceans created by tidal heating? And are there any parallels that we can draw or infer from the similarities between Europa and Enceladus?
There are a tremendous amount of parallels that we can draw. They are, in fact, both heated by this mechanism of tidal flexure, which is why they have oceans within them, and both of them have oceans. And I would say it goes the other way, that we have been nearly a dozen years now exploring up close and personal Enceladus with the Cassini mission, and with an amazing suite of 12 investigations on the orbiter that have been brought to bear over the course of those dozen years. And we know a tremendous amount about Enceladus, really far more knowledge about Enceladus at this point in time than we do about Europa. But I'll turn this over to Chris, because Chris also has a lot to say about this topic. So what do you have to say?
Well, imagine sometime in the future when we find life on Enceladus, we find life on Europa. Are they the same life? Do they represent a common origin? Or did life start independently on both of these water worlds? Or did life start on one and not the other? So I'm always focused on the biology questions, and a comparison between worlds is the most interesting possibility in terms of what kind of questions we can ask about biology and compare these two water worlds. And then, of course, we'd want to compare them to Earth as well.
Yeah. And let me just remind people that why we've gone so goo goo gaga over Enceladus, and that is because we found that it has 101 tall geysers that are erupting from its south polar terrain, which is an area, if you were to scale Enceladus up to the size of the Earth, it would be like the latitude of Tierra del Fuego and everything south.
Wow.
Or if you were biased towards the Northern Hemisphere, it would be like Edinburgh, Scotland, and everything north.
Wow.
So imagine having 101 enormous geysers erupting from the terrain that's that large. And once we found with Cassini these geysers, and we knew that the particles that we see in our images were accompanied by vapor, and they formed this enormous plume that went ultimately tens of thousands of kilometers into orbit around Saturn. We took Cassini and we went barreling through it. We went barreling through it time and time and time again. And we've been able to collect material and measure the contents of the vapor, measure the contents of the particles, measure the characteristics of the particles, how big they are, how their size is distributed above the surface. And all this information has finally told us where we are right now. We know we have a global ocean under about 35 kilometers worth of ice. It's salty. It's salty like the Earth's ocean is salty, and it has organic material. So it's got all the formal requirements of what in the NASA world, the NASA universe, we call a habitable zone. And that ocean is accessible now. All we have to do is fly through it again with the proper instruments, better than we have on Cassini, to measure it with a greater precision, and start asking really interesting astrobiological questions. Chris, what are some of the things we could do if we had a mission that went back to Enceladus with proper instrumentation? What kinds of questions do we really want to know?
Well, I think you said it well, Carolyn. We already know it's habitable. We already know it has organic material. We already know it has liquid water. We know that liquid water is habitable. So the follow-on questions really go right to the biology. Is it inhabited? Does it have life? And then the challenge is, how do we search for life? Well, we can search for life using molecules and tools that we develop for characterizing Earth life. But it'd be nice to also have a capability to detect life if it's not Earth life. So then the question becomes, how do we detect life that's similar to Earth, lives in water, made of carbon, but is not directly related to us, doesn't have our DNA? And I think the answer to that is to search for amino acids and search for their handedness and see if there is a enrichment of heavy, complex amino acids in the plume of Enceladus. and then to see if those amino acids all have the same handedness, which is a clear signature of biological selectivity.
When you, from an astrobiological standpoint, what would be more desirable? To analyze these components flying through these plumes, or capturing the water and bringing it back?
Good question. That's a very, very good question. There are people out there, groups of people, one group I know of that are looking at the possibility of a sample return. It's not a trivial thing to do because there's a lot of concern if you bring a sample back to Earth. You don't want to have an Andromeda strain scenario where you contaminate the Earth. So, that has to be done carefully. But
those Earthlings were really something special until they brought back that old Enceladus water.
Really, that was the beginning of the end. The instruments that we have on Earth are far more sophisticated than the ones that we could carry on a spacecraft. So. So Chris, in fact, has been a big proponent of a sample return mission.
But as Carolyn points out, one has to be extremely careful in bringing back a sample from an environment that we think could have life in it. And that environment is very similar to Earth's ocean. We've never done that before. We've brought back samples before, but we've never brought back a sample from a habitable environment. So this is a new challenge, and we have to proceed extremely carefully with it. So I think the next missions to Enceladus will not be sample return. They will investigate the plume in situ, following up on Cassini, but they will be designed to search for life, unlike Cassini. Cassini did a fabulous job. It was a wonderful an unexpected find, and its ability to investigate it surprised all of us. And now we're back with a mission that's based on what we know and search for life in the plume. And then, meanwhile, think about how we bring a sample back safely, because ultimately we have to do that.
Yeah, can I just make a plug for Cassini? Because as Chris said, the instruments on Cassini that were really, the cameras, can take a picture of anything, but the instruments that told us about the chemistry were not designed to investigate a plume of material that was as tenuous as that which is coming off the south pole of Enceladus. They were designed to measure the atmosphere of Titan, for example, which is much more hefty. So it was a beautiful demonstration of how important it is to, first of all, be in orbit and kind of take up residence in a planetary system so you have the leisure of discovering something and then going back to investigate it again and again and making changes in your approach.
Right.
And that's what we did with Cassini. But I want to add just one more thing about Enceladus, which fascinates me. 94% of the stuff that's being erupted from the South Pole of Enceladus, the particles, not the vapor, but the particles, comes back down to the surface. Right. It snows back down to the surface. So if there are microbes in the ocean of Enceladus that are being shot out, it's snowing microbes at the South Pole of Enceladus. So I think another thing we want to do is we want to go sample those particles and see if there are microbes in it. That's what I get really excited about.
That's pretty cool.
It doesn't get any cooler than that.
That's a holy grail. That's pretty fun. Now, and what do you do when you do that? Is that putting instrumentation down on the surface?
Well, this is very interesting. Yeah. We've all been discussing this. We're discussing how you might actually do this. And it just occurred to me recently, you don't need to land on the surface.
Okay.
All you need to do is really get into orbit around Enceladus. And the speed with which you pick up these particles would be gentle enough that you would not destroy microbes that were in the ice particles. And that's what we want. We'd love to be able to take a look at them. Now, whether or not we have the instrumentation now to do it is a question. Maybe, Chris, do you know something about this? The capabilities of microscopic imagers to do this sort of thing?
Actually, as you point out, we don't have a heritage in planetary missions of searching for life. We haven't done that since Viking, 1976. But meanwhile, NASA and other organizations have been developing technologies for studying life on Earth. There's been satellites in Earth orbit that have looked at biology, and these life sciences technologies can be applied to the search for life and be made suitable for planetary missions.
Life sciences technology?
Yeah,
what do you mean by life sciences tech? That sounds oddly like like a life coach.
No, not that. What I mean is
not lifestyle, not a lifestyle.
Not a lifestyle. Like what is the life sciences? Go ahead.
Well, we can think of two different jobs that we might do in space. One is take life from Earth and study it in space. That's called life sciences. The other is search for life on other worlds, life detection. They're both centered on life, but in one case, you're taking life with you and studying it. The other case, you're going somewhere and seeing if there's life there. But for example, a fluorescent microscope would be handy in both cases. Well, there's not been the development of such a microscope for planetary, but there has been for life sciences. People have taken these kind of instrumentation into orbit to study organisms that they've carried with them to investigate the response of these organisms to the space environment. We can take that technology and repurpose it to searching for life in the plume of Enceladus.
Oh God, that's so
great.
It's so exciting. I can barely stand it.
That is
really. It's like there. It's waiting for us to go back.
Super cool. Super cool.
So we're going to have to wind down now. And thanks to our co-host, Chuck Nice. It's been a pleasure. Chuck.
Oh, the pleasure's all mine, Carol.
And thanks to Chris McKay, who's joining us from Ames Research Center for his insights into the origin of life. I've been listening to Star Talk Radio All-Stars Edition. I've been your All-Star host, Carolyn Porco.